Welcome. My name is Chiara Bartolozzi, and I am a researcher at the Italian Institute of Technology. In this presentation, I want to give you a small glimpse of the activities of the Event-Driven Perception for Robotics group towards the integration of event-driven vision sensors on humanoid robots. So this is the scenario that we imagine in the near future. We would like to have robots that autonomously interact daily with us in an environment that is, by definition, dynamic and unconstrained. And to do so, our idea is to exploit the characteristics of event-driven vision sensors. And in particular, what is very important is that these sensors can encode information very efficiently. And we can exploit this type of encoding that lead to very low latency in the transmission of information and also to a very low power and efficient computation, with the goal of having online systems that run on the robot at a very low cost. So the platform that we have been using is the Neuromorphic iCab. iCab is a platform designed for research in humanoid robotics, where we have the possibility of integrating any new technology we want to try it out in different tasks. So what we have been doing was to integrate event-driven vision sensors in the robot, and they are now integrated in the eye. So we have binocular event-driven vision, and specifically the current version of the iCab has the ATIS Gen 1 sensors, and we are slowly moving to integrating the ATIS Gen 3 together with frame-based sensors. At the same time, we have integrated also different computational platforms, starting from FPGAs for acquiring the sensors with very low latency and with a very tight control on the events that we get, and so that we can check if we lose them. We use CPUs and more recently also GPUs for doing computation, but also neuromorphic hardware that is integrated using the event-driven library based on YARP, the robotic operating system, that allows us to have a very modular system with different processing running on different hardware platforms that are very, very different in terms of capabilities, so CPU, GPUs, and neuromorphic hardware. Here you see Spinnaker in this case. So we have different modules running on the different platforms that communicate constantly with each other in a way that we have a very flexible system. So what did we do in terms of developing event-driven vision on the iCab besides integrating the sensors on the robot? Well, first of all, one very interesting aspect is to look at mechanism of attention and selection of interesting region in the field of view. So this is a mechanism, selective attention, that has been observed, is well known in humans, so that interesting regions of the field of view are selected in a sequential way and processed with very high resolution. And in humans, what we do is to move our eyes, our fovea, that has the highest resolution of sensing elements, towards the important region in the scene. This is a way to optimize the computational resources so that we sequentially allocate them to interesting parts, very interesting or relevant or informative parts. And this is a very useful mechanism that we can also apply in robotics. Then another method in computer vision that is very popular is to detect informative features in the field of view. For example, we worked on online corner detection because corners are highly informative regions of the visual input that we can use, for example, to compute motion, solving the aperture problem, and also, for example, running stereo matching for depth perception and other algorithms. Once we have detected interesting regions, since we are dealing with a very dynamic environment with objects that can move, what is interesting in robotics is to track the objects that move so that the robot can interact with them. And here it's very important, the characteristics of the event-driven vision sensors that basically have a continuous trace of the object in space. So if the object moves of 1 pixel in the visual space, it immediately triggers an event. And therefore, we have a continuous trace without having the problem of the correspondences. Once we have tracked the object, we want to, for example, predict where this object is going to be in the near future. This is because once we know that the object is moving and we can track it, the robot still has to plan for the correct action to perform and execute the action. And this takes time. So if we can have kind of a prediction of the near future, the robot has the time to plan and execute the action to interact with dynamic objects. So in this presentation, I'm going to touch on these 4 topics, actually on 3 topics, because I'll skip the tracking as there are a few presentations around already on the work done on tracking. So we start with attention, and the work we have done is based on stimulus-driven saliency computation. So basically, we want to look at models that understand which are the interesting regions of the input solely based on the physical characteristics of the stimulus. And this doesn't have anything to do with the task that the robot or the person has to perform. And the model that we use are based on the concept of the saliency map. So a map that encodes where in each, the kind of how salient, how interesting, how informative it is, a point in the image. So for example, here in this picture, what you can see is that you have a red dot in this position, and this means that here you have a peak in the saliency map, and that's where the robot should look at and inspect with high resolution. Given we are working with robots, we focus our attention on 2 concepts. One is the Protoobject. We want the robot to be able to select regions where there could be an object, as objects are usually the things that the robot is interacting with to accomplish a task. And also we wanted to look at the depth information because, again, something that is close to the robot is something the robot can interact with because it might be reachable or it might be threatening. And so we want to give saliency, perceptual saliency, to objects that are close to the robot. So we started from a bio-inspired model of attention. This model has been, is kind of the last version of many models that have been proposed starting from the 2001, the model proposed by Etienne Koch. And this is, the latest developed by the group of Ernst Niebuhr at Johns Hopkins. And it's basically based on processing the image along different information channels. We have intensity, color opponency, orientation, and in this case, also depth. In these channels of information, basically what happens is that where there is high contrast in a certain feature channel or feature map. So for example, where I have a red hat in a gray image, or I have a tilted bar among horizontal bars, then these stimuli capture attention, have high saliency. But in this model, there are other two very important features. One is depth. As I said, they use both RGB images and depth images, and the concept of grouping. This concept of grouping basically looks at the feature maps and looks at where in a feature map there is something that can be considered an object, so a proto-object. The grouping is performed by performing edge extraction on a certain feature map, and then creating border ownership cells that are based on the von Mises filter. These curved filters basically tell you if a region, if an edge in the image belongs to a certain border, and then different von Mises filters, all oriented having the same center, are grouped together in a way that closed contours or partially closed contours form the concept of the proto-object. So we started from this model, but this model is based on RGB images and on depth images. What we did was to convert this into an event-driven system. So first we looked at the intensity channel and implemented the proto-object extraction model, and then we looked at the depth channel. So in this work, we have taken the output of event-driven cameras, separated positive events from negative events. In our implementation, we don't need to run the edge extraction because this is done already by the event-driven cameras. Then we implement the von Mises filter border ownership parameter and then the grouping parameter. In this system, we have scale invariance given by the 5/11 of parameters, and also we have very high speed because the model can select a stimulus that is moving at 2000 pixels per second. Now, if we consider this stimulus, where on the left we have just oriented corners, and on the right we have oriented corners that in this case for an almost closed contour. If you see, this almost closed contour to us is perceived as an object and is immediately pops out. It's immediately detected by our attention system. So the model proposed by the group of Ernst Niebuhr that doesn't take into account the depth is the kind of the former model without the depth channel proposed by Russell and colleagues, using RGB input images, sees that there is a clear selection of the closed contour with respect to the non-closed contour in the left image. And the same happens in the event-driven implementation of the same model that I showed you in the slide before. And in this case, instead of using RGB images, we basically took the image and shaken the image slightly in front of the sensor so that we can generate events from a static picture. Then, as I said, we moved to the implementation of the disparity, the depth channel. In our case, we don't have a disparity image from the RGBD sensor, but we have a binocular vision system. So we use the left camera events and the right camera events and a disparity extractor that generates a disparity map. Then the disparity map is fed as input to the border ownership and grouping mechanism, so the proto-object part of the model that we implemented before. The disparity map has been implemented following the previous implementation by the group of Jörg Conrad, that is based on the cooperative stereo matching model. Basically, this model exploits temporal proximity of events, and inhibition and excitation along different dimensions of disparity maps, in a way to remove the problem of false correspondences. So this is okay. So in the next slide, in this slide, I'm showing you the qualitative results. So the model is running on the robot, and here you see Julia, who is moving her hands in front of iCub. And here you have the events from the left and the right camera in red and blue. Where you see yellow is because you have multiple events in the same pixel in the time frame that we use for the visualization. We have the online disparity map, where you see the color changes depending on how close the hand is to the robot, and the corresponding saliency map. And you can see that it jumps from the left and the right hand depending on how close, on the closest one. What you see here is basically the x coordinate of the maximum of the saliency map, and the position of the events of the left hand in the x coordinate and of the right hand. And you can see that the maximum of the saliency map jumps from the left to the right, left, right, every time there is a switch between the two hands. This happens when the robot doesn't move the eyes, but since we want the robot to be able to also perceive static elements in the scene, we add some small wiggling of the eye of the robot so that we elicit events also from the background. What you see here is that the system is still quite robust to what is closer, but we have some peaks, some selections that depend on the fact that there are other proto-objects in the scene that are close enough to elicit a certain saliency peak. And if you see here, the saliency map taken from the field of view of the robot, you can see the background events from the desks and also the background events generated by Julia. And we have a peak here that is exactly in between the X positions of the left and right hands that corresponds to the head that actually is detected as a proto-object. So in this case, we have a system that can run on the robot online and that can tell the robot where to look at. And for example, we can select the maximum of the saliency map to orient the gaze, so performs a CAD, and then perform recognition of the region of interest with object recognition pipelines. The future of this work is to augment the information that we feed to the system, for example, looking at orientation and at motion, and we are implementing this system on neuromorphic hardware to have a low latency system that can run online on the robot. So the next part of the slide is about feature detection. As I said, corners are in general in computer vision very salient and important points to process, and there have been a lot of work on corner detection with event cameras. And here I present the latest that we very recently submitted, where we try to have a system that runs online with the new cameras that have a much higher event throughput, and that tries not to trade off online performance with accuracy. So doing a step back, this is a representation of how the E-Harris, so the first corner detection algorithm that was proposed to run on the event stream works. So basically, for each event in the event stream, there is a data representation that is updated. And so for each event, we take a close neighborhood of the sensor and put a black dot where we had event in a certain temporal window. Then on this small patch of the visual field, we implement the Harris corner detection algorithm that basically means we convolve the patch with a Sobel filter and then compute the Harris score, put the threshold, and decide if the event was belonging to a corner or no. And then an output event is emitted that is at this point a corner event, and we have a corner stream. Now, this algorithm is kind of slow because it's serial. You first have a data representation event by event, and for each event, you first do the data representation, run the algorithm, and then decide if the event is a corner or not. So the performance depends on the number of events. The higher the number of events, the slower the algorithm is. So there have been works that tailored the online application of corner detection using this type of pipeline. They improved the data representation and the algorithm without using Harris anymore. So for example, ARC proposed by Al-Zukarai and FAS proposed by Elias Mügler of the group of Davide Scaramuzza, they basically substituted the algorithm to have something that was lighter. But in this way, they kind of traded off the online implementation with the accuracy of the corner detection. And still the full algorithm depends on the number of events. So what Aaron has been doing lately was to try to basically have a different infrastructure whereby we decouple the data representation that is updated event by event very quickly from the algorithm itself. So basically we have a data representation called the threshold ordinal surface, where every time an event arrives, it adds. So every time an event arrives from the event stream, the maximum value is associated to the corresponding point to the threshold ordinal surface, and the neighbors are decreased of 1. And then the whole image is thresholded so that pixels that have a low value are sent to 0. So we have very clear representation that can be then fed to the Harris detection algorithm. This algorithm runs as fast as possible on the latest version of the TOS surface. And in this way, we can easily call the OpenCV implementation of Harris that runs decoupled from the data representation. Then for each event that arrives, we can query the output of the Harris implementation and decide if in that point the value is high enough, crosses the threshold to classify the event as a corner. So the algorithm runs as fast as possible, always on the latest representation of the data. And in this case, we also avoid having to fix a temporal window parameter. And we also don't discard events, but always get the most up-to-date representation. So in this slide, we have a video with the representation of what is going on with the event stream, the threshold ordinal surface, the corner score lookup table that is generated by the OpenCV call. And here you have the videos of the results of eHarris, IUV Harris, ARC, and FAST given a certain dataset input. In this case, it's a shapes dataset. And here we have synchronized the videos of the output. Also in this case, we're using the boxes dataset. We synchronize the output to compare qualitatively the traces of the corners. And you see that in LUV Harris, they are very stable, very thick and nice, and they can be easily tracked. Here, what you don't see is the delay that each algorithm has. Here is the maximum number of events that each algorithm can support running online. And here you have a video of the LUV, ARC, and FAST for a certain input running online. And here you have the mean, kind of the instantaneous event rate. And here you see when it crosses the 5 million events per second, 10 million events per second, and so on. And you see clearly that the LUV is online and has only very few milliseconds of delay, while ARC and FAST accumulate delay when the events cross the 5 million events per second. So this is just to show that we have, yes, good results that can enable online corner detection with the newest cameras that have much higher event throughput. We removed the need of the temporal window, and we can still use Harris that has higher accuracy than the other algorithms. What is interesting here is the method of decoupling the data representation from the algorithm call. So as I said, we are not going to talk about tracking because this has been covered in different presentations, but I want to concentrate on the prediction. So the idea is to enable the robots to interact with dynamic objects. And tracking is not enough. It would always be lagging, following the tracked object. But prediction is very useful because it gives time to the robot to plan for the action. So the question here is, do event-driven vision sensor and asynchronous sampling of the information, very high temporal resolution, give an advantage when we want to predict trajectories of moving targets? So we considered a very simple use case as a proof of concept of the whole system. That is a bouncing ball. This is kind of the superposition of different frames of a frame-based camera looking at the ball bouncing on a table in our lab. It's kind of difficult from these samples to see that there is a ball moving. It's static, so probably if you would see the animation, it would be easier to understand. But what you can see here is that the sampling doesn't have much to do with the trajectory. Sometimes you see motion blur, so you see that defocus of the ball when it's moving too fast with respect to the frame rate of the sensor. And the difference is very striking with event-driven sensors. So what you see here are in purple the events generated by the ball, and in blue the center of mass of the events over time. This is accumulated over the whole trajectory. So here, you don't really have motion blur. If you look at the correct temporal window, you would only see really the edge of the ball. And you can really see the trace of the center of mass of the ball tracked that is continuous in space. So is this useful at all? Is it easier to predict where the ball is going to be if we use an event-driven vision system or not? To do so, to answer this question, we have used this pipeline where we have the ATIS camera mounted on the iCab robot. In this case, we use a single camera. We don't do binocular vision. We have a tracker that gives the center of mass of the ball over time. It's asynchronous, so you can, every time the center of mass of the ball moves it generates an event of with the coordinates of the center of mass and the timestamp of the center of mass. And then we use an LSTM encoded decoder architecture to predict the next parts of the next part of the trajectory. We use the LSTM as it's kind of the state of the art in networks that can predict temporal sequences. So we have trained the system and used validation and test set, and this is the result. So basically, we have in dashed blue the ground truth trajectory of the ball in a space that is x, y, and time. In green, you have the input given to the network. It's 15 points. And in purple, you have the output prediction of the network. That is 35 points. And what you see is that the system quite well predicts the ball. It doesn't have any knowledge about the bounces. So it knows that sooner or later the ball is going to jump. So it starts predicting that there is a jump, but it doesn't know when there will be, because it doesn't know the position of the table with respect to the trajectory of the ball. But as soon as the ball jumps and the system sees one event of the new trajectory, the update is very low latency, and in 1.5 milliseconds, the trajectory goes back to the correct prediction. So we went further in looking at the output of this network and analyzing this output. So we had a look at what is the difference, is there an advantage between synchronous systems and asynchronous systems. So in synchronous systems, you can sample the trajectory of the center of mass of the ball every temporal interval, every fixed temporal interval. So every 30 milliseconds, every 10 milliseconds, irrespective of the trajectory and of the movement of the ball. Or you can have an asynchronous sampling that is a space-based sampling in this case. So we can look at the output of the tracker of the center of mass of the ball whenever the center of mass of the ball moves of a certain space quantity. So it can move of 1 pixel, so we have a very dense trajectory. We can output the event when the center of mass has moved of 2 pixels, of 3, 4, 5, 10 pixels. And in this case, we have an asynchronous sampling, because it doesn't depend on time anymore, but on the speed of the ball. So here you can see a table where basically you have the special delta at which you sample the output of the tracker, like 2, 4, 6, 8, 10, 12 pixels. And here you have the corresponding mean frequency that would be similar to the 2 pixel sampling, for example, if you would sample at fixed rate. We have a very high standard deviation because the trajectory of the ball has different velocity. And this is also the number of times we would call the LSTM network if the tracker output is read every time the center of mass of the ball moves of 2 pixels. So the denser the spatial sampling is, the more often we call the LSTM network, and therefore the more costly in terms of computation is the algorithm. So we had a look at the average spatial error of the prediction of the trajectory for changing the spatial sampling in the asynchronous sampling strategy, and for changing the temporal sampling for a synchronous system. In this case, we are comparing two systems with two different sampling. The synchronous one is very similar to the frame-based cameras, but the tracking is still done with the events. So we are not evaluating the tracking performance that might be worse in frame-based systems. And what you can notice is that for the asynchronous sampling always performs better. And for increasing the density of the spatial sampling, so going towards higher rates, the error decreases, of course. But in terms of computation, if we want to trade off the computational cost and the performance, even lower sampling rates are acceptable. So this is kind of answers the question: is it interesting? Does it give an advantage to use asynchronous event-driven sampling or vision for prediction? Well, the answer is yes. Now we want to use this system on a robot to interact with a moving object. And this is kind of a preliminary result using the Panda robot that needs to intercept a bouncing ball. In this case, we are not really we had to modify the prediction because it's not so interesting for the robot to predict the dance trajectory right after the first points observed in the trajectory, but it's more interesting to look at the trajectory and predict where and when the ball is going to be in this space where the robot can interact with the ball. So if you look here, this is sorry, I use the laser pointer. If you look here, here is what the cameras that are mounted here see of the visual space. And the robot can move up and down in this coordinate. So what is important in the predictor is I observe the trajectory, the ball starts here and bounces. What I'm interested in is where is it going to cross this space and when, so that I can move the robot. So in this case, we change the LSTM. It's not anymore the one that we used at the beginning, but we use a stateful LSTM. So basically, the LSTM network now gets the input every time you see the thickening of the green arrow. It means that there is a new position of the center of mass, and the LSTM network outputs the prediction of the position in time and space of the ball, and updates its state. Then it's fed back. And the network keeps doing this indefinitely unless you reset the memory. And we reset the memory only when we know that the trajectory is over. So for a single trajectory, we keep updating the input of the LSTM network and updating the prediction. And it turns out, it's anecdotal, we are still kind of analyzing the results, that the more you wait, the better the prediction is. And also that with the asynchronous sampling, the convergence of the prediction within a certain error boundary happens faster than in synchronous systems. And so we can, wait until the very last moment when the robot has to move to intercept the ball to get the best prediction and a good behavior of the robot, a good performance. So here you see the first attempts to run the system. So the video should start, but it doesn't. So sorry, but apparently I don't manage to run this video. You will have probably to watch the live presentation during the CVPR workshop. So, I mean, the conclusion of the previous work was it's useful to have this asynchronous system, and now we need to put together the perception with the control of the robot and find the best strategy. So to conclude this presentation, I try to show you different types of approaches on how to use event-driven sensors and how they could be useful in humanoid robotics applications. The message is we are still at the development of vision, of perception, and methods to extract information so that the robot can move in an appropriate way. And we are tackling different aspects of vision that then altogether will be the basis for using event-driven vision sensors on robots. But vision is really not the only thing we can do with neuromorphic hardware and technology. What you saw is also we can use neuromorphic computation running. What we saw so far was running on CPUs or GPUs. And we are working on the implementation of the things you saw during this presentation on neuromorphic hardware. Here you see Spinnaker, but we are also integrating online Loihi, and we are working with the group of Giacomo Mendiveri for integrating Dynops. This is not yet the whole story, but we are also working on auditory perception. In this case, we collaborate with the University of Sevilla for including spiking cochleas in the robot for sound source localization, but we are also looking at auditory visual speech detection, speech enhancement, and all processing of the auditory signal that might be useful on a robot that needs to interact with people. And then what is also very interesting is to work on touch. You might have seen presentations about neuromorphic tactile systems. In the case of humanoid robots, like the ICA, but also few other platforms, tactile sensors are used in the fingertips, where you see black here, for object manipulation. But in the case of ICAB, for example, where you see black, you have a surface that is completely covered by tactile sensors, and these are very useful for the perception of the robot when it's interacting in the world, to detect contacts, to detect the exchange of forces with people or objects it's interacting with. So it's very important, but the point is that we have more than 4,000 sensors distributed in a large surface, and these are sampled every 10 milliseconds. So it's really a huge amount of data. If we use event-driven type of sensing, it means that the sensors will only communicate data when there is a contact. And the contact in a tactile system of the robot is really localized in time and space. And therefore, only the few taxels that are active during a contact would send data that is very highly informative. And therefore, we can really exploit the low latency and high compression of the signal given by event-driven sensing. So in the future, I think we should move towards the integration of more and more sensory modalities implemented with event-driven technologies on humanoid robots, and at the same time work on the communication. Because in robots we have the problem of wiring of space, and therefore it's very interesting to work on asynchronous serial communication to have a single hub that then can integrate information from different sensory modalities with single temporal reference. So with this kind of idea of the future, that would also then include moving the robot using spikes, I want to thanks the whole group that is really supporting my wild ideas about what can we do with humanoid robots and event-driven sensing. And of course, I have to thank for the support, the funding from the European Commission and the different groups, mostly around Europe and Italy, that are collaborating with me towards the goal of integrating event-driven and neuromorphic technology on the robot. Thanks a lot for your attention, and I hope to see you at the CVPR workshop.